Assalamu alaikum. Welcome to the lecture second of unit second, that is AC to DC converters. Today's topic is single phase half wave uncontrolled rectifier for different types of loads. And firstly, I'm going to teach you single phase half wave uncontrolled rectifier for our load. This is the circuit diagram of single phase half wave uncontrolled rectifier for our load. This is the most simple AC to DC converter. Since we have to convert AC to DC, that means at the input side we have one source voltage that's represented by Vs is equal to Vm sine of omega t. This is one diode, that's a semiconductor switch that's used for rectification, and since we are using diodes, that's the uncontrolled, that therefore the rectification here will be uncontrolled rectification. This is the resistive R load. In case of resistive load, our voltage and current, they are in phase. While as in case of inductor, in case of capacitor, either the current leads voltage or current lags voltage. This is a simple equivalent circuit of a uncontrolled half wave rectifier. Here we have to represent that by different types of waveforms. That means since here at the input side we are applying a sinusoidal voltage that is represented by Vs is equal to Vm sine of omega t. This is a sinusoidal waveform and the voltage is varying with respect to omega t, or we can say we have peak at omega t is equal to 90 and omega t is equal to 270, where 0, pi and 2 pi they are at 0. That means, and this cycle goes on repeating. That means this is the first cycle and this is the second cycle. Since we know that here the driving force is source voltage, that means when there is voltage present in the circuit, there will be if the circuit is closed, then there will be current in the series circuit, and accordingly there will be some voltage across the load. If the circuit is open, then there will be no current in the circuit, and accordingly there will be no voltage or current across the load. These are the waveform. That means this V naught represents the voltage across the load, I naught represents the current across the load, Is represents the source current, and Vd, that is the voltage across that semiconductor device. Since here we are studying that uncontrolled rectifier, that means here we are using a simple diode. In case of diode, this Vd represents the voltage across the diode. Here we have made some assumptions while teaching. We have made some assumptions that here this source voltage, that is purely sinusoidal. Another thing is that this semiconductor device is also ideal. That means during conduction, the voltage across this is basically 0.7 volt, that is taken as 0. The leakage current, or during reverse, when reverse voltage is applied across this diode, that leakage current is taken 0. And here the third assumption is that the circuit parameters, that is inductor and capacitor, they are ideal. Single phase half wave uncontrolled rectifier is also called as one pulse converter, because for a full cycle we are getting only one pulse. That means for a full 360 cycle we are obtaining pulse for only 180. That means here output, if you see that here the output voltage is only for half cycle. In the next cycle the output voltage is only for also half cycle. That's why it's called one pulse converter. Since we are applying sinusoidal voltage, that means we have positive cycle and negative cycle. Now we are analyzing the circuit for the positive half cycle and for the negative cycle. From omega t is equal to 0 to pi, basically our source voltage, there is some positive, that means some positive voltage, or we can say across this diode, this anode is positive, anode terminal is positive with respect to cathode. Every time we have to consider the anode terminal with respect to cathode. That means since here anode terminal of diode is positive with respect to cathode, this diode is conducting, or we can say the diode behaves like a short, or driving source is the voltage. That means there will be some current in the circuit, and that current is represented by I naught across the load, and this I naught either you represent it by is or I naught, that is the source current or series current across. That means this I naught is equal to is in this circuit. If you apply the KVL here, minus Vs plus Vd plus V naught is equal to 0, or we can say, finally, we can say this Vs is equal to V naught, or voltage across this load that is represented by V naught is equal to Vm sine of omega t. Moreover, as already explained, that we are using that ideal diode. That means voltage drop during its short 0.7 volt, but that's almost negligible as compared to source voltage. That means this voltage across diode is 0. However, during negative cycle, that means from the period that is omega t is equal to pi to 2 pi. That means since our source voltage is reversing, this is the graph. That means from 0 to pi it's increasing, pi to 2 pi it's decaying, till at omega t is equal to pi it becomes 0, and after that omega t, beyond this omega t is equal to pi, this source voltage is basically, we are saying, this is increasing the negative side, or we can say that means this is negative and this is positive. That means this is negative, this is positive. And when this, that means across this diode, since we have to consider anode with respect to cathode, that means anode is negative with respect to cathode, or you can say cathode is more positive with respect to anode. And because of that, we are saying diode behaves like the open circuit. Diode is reverse biased, and that's represented here by open circuit, or you can say in that series path, since the circuit is open, no current flows in the circuit. Since no current flows in the circuit, that means voltage drop across this load, that is I naught into R, is equal to, since I naught is 0, that means V naught is equal to 0. Or we can say across this open path, the voltage across this diode will be equal to source voltage. That means during this negative cycle, the source voltage is equal to, that means the voltage across diode will be equal to voltage across source, and this V naught is equal to 0. Similarly, I am representing it here from during positive cycle, from omega t is equal to 0 to pi, our output voltage is equal to source voltage, and voltage across diode is 0. And similarly, during negative cycle, that means from omega t is equal to pi to 2 pi, this output voltage will be equal to 0. While analyzing, that means from during positive cycle there will be some current, and during negative cycle there will be no current, and that's represented by the wave shape in this I naught waveform, where I'm saying in positive cycles there is some current, in positive cycle there is some current, whereas in negative cycles there is no current, and that's represented by this bold line, that is 0. The wave shape is exactly same as that of source voltage, because this is the resistive load, and in case of resistive load, that means the current and voltage, they are in phase. That means this is the source voltage. It will start, if the source voltage start from 0, this will start from 0. If it reaches at omega t is equal to 90 at its peak, similarly here in case of I naught, it will reach its peak and then back to 0. That means this is at omega t is equal to pi, it will be again back to 0. That means since the driving force is source voltage, this current in this circuit is because of this driving force, that's your source voltage, and that's why I'm showing, if I'm saying, if source voltage is present in the circuit, there will be some current. The only difference is lies in the only difference here is that the peak is slightly lesser, that is equal to, if this is Vm, this will be Vm upon R in case of I naught. Since this is the source, since this is a series circuit, here the source current will be equal to I naught. That's why I am showing here I naught is equal to I. That means this is the wave shape of also source current. Now, if there is a current in the circuit during positive cycle, that means there will be some V naught, and that V naught will be equal to I naught into R. That means if there is a driving force, there will be current, and because of that current, there will be some V naught. Having exactly same peak at omega t is equal to pi equal to Vm, and at omega t is equal to 0, V output will be 0 because the source voltage is 0, the current will be 0, and this output will be 0. Now that means during this negative cycle, again this output voltage will be 0. This is another negative cycle, the output voltage will be 0. Similarly, as I have already represented in that analysis part, that during on condition, that means during turning on or during this positive cycle, where our diode's anode terminal is positive with respect to cathode, that means this voltage across diode will be 0. That means whenever this diode is conducting, this voltage drop is ideally 0 volt, and practically that is 0.7 volt, and that's almost negligible. This is represented by the zero line, bold line. I mean, this is voltage drop. And as already represented in the analysis part, that during this reverse bias, that means from pi to 2 pi, this voltage Vd, that's equal to our source voltage. That means that's why here this wave shape, this follows this negative cycle. That means when Vd is equal to Vs, that means that's why I am showing this is the negative part. This is following this cycle. During positive cycle, I have already represented in the analysis part, that means diode is conducting. When diode is conducting, voltage drop across that will be 0. Again, I am showing it as 0. And during negative cycle, where diode is reverse bias, this Vd will be equal to Vs. That's why I am showing this follows the negative cycle, that is the source voltage. These V naught, I naught, Is, Vd, all these wave shapes are basically, they are formed because of this driving force, that is the source voltage. When the source voltage is present, if the diode is short, then there will be current. If the diode is open, then there will be no current. Also, this converter is called one pulse converter because for a full cycle we are obtaining only one pulse. That's why one pulse converter. Now the mathematical part, that means from that waveform we have to obtain the average value of output voltage, average value of output current, RMS value of output voltage, RMS value of output current, and other expressions like peak inverse voltage and extra. Firstly, this is the average value of output voltage. That means since we know that the average value of output voltage, that means this is this will be equal to 1 by 2 pi from 0 to 2 pi, that is V output d omega of t. And since we know that we have this from 0 to pi, our diode is conducting, pi to 2 pi, our diode is not conducting. And similarly, I have divided it into cycles, that means 0 to pi, that means this is V output d of omega 2 t, plus pi to 2 pi, V naught of d omega t. Since we know that, since the output voltage as voltage during on cycle, there will be, that is equal to source voltage. That's why I am representing here V output is equal to Vs d of omega t, and output voltage during negative cycle is equal to 0. That's why I am representing this by 0. This is equal to source voltage. That means this represents this positive cycle, and this represents the negative cycle. That means this is equal to 1 by 2 pi 0 to pi Vm sine of omega t, till we are saying this V output is equal to Vm upon pi, or 0.45 Vs. Similarly, we can get the average value of load current, that is equal to I naught is equal to V naught upon R. Similarly, I have written here I naught is equal to Vm. This is the value of V output voltage divided by Vm pi R. Similarly, what will be the value of RMS value of output? That is equal to Vm by. Next one is RMS value of the load current, and similarly, since we know that what's our output voltage RMS, that RMS value of current will be equal to output voltage RMS divided by resistance, that is equal to Vm by 2 R. Power delivered to load, that is equal to P naught, that will be equal to V naught V square by R, or I square into R. Similarly, we have to obtain that input power factor, and since we are using here ideal diode, that means losses will be equal to 0, and this P input will be equal to P output, or we can say this cosine of this phase angle is equal to V output RMS upon source voltage. Now we have one more term, that is the peak inverse voltage. Peak inverse voltage of a diode is basically the maximum voltage that appears across the diode during its blocking state. That means on that this diode breakdown of that diode may occur. Just like this wave shape, it is the maximum reverse voltage that a diode can withstand. That means this peak inverse voltage in this single phase half wave uncontrolled rectifier is equal to Vm. What's this conduction angle? This conduction angle is represented by gamma. In every case, for L load, for R load, for RL load, RLE load, you have to take care of those things. That means peak inverse voltage is represented by PIV, conduction angle by gamma, extinction angle by beta. That means what's the conduction angle? It is the period during which diode is conducting. As we know, here diode is conducting from 0 to pi, then here conduction angle will be equal to pi. Shown in this diagram, this conduction angle, because the diode conducts from 0 to pi, and from pi to 2 pi it's reverse biased. Now another one is that extinction angle. What's this extinction angle? It's basically up to which angle we are getting this current. Here this extinction angle, that means we are getting current up to this pi. That means this extinction angle, this from 0 to pi, this extinction angle that is represented by beta, in this case it's equal to pi. This is in case of single phase half wave rectifier. Here gamma is also equal to pi, beta is also equal to pi, or we can say in this case gamma is equal to beta, that's is equal to pi. But that's not possible in every case, in every load. In only this single phase half wave rectifier, we have gamma is equal to beta is equal to pi. Another one is that is circuit turn off time, that's represented by TC. Here this is the circuit turn off time, represents the time for which our diode or semiconductor device is reverse biased. Here this basically this diode is reverse biased from pi to 2 pi, or we can say that period is 2 pi minus pi, that is equal to pi. Or this is represented by, this is omega TC is equal to circuit turn of time is equal to pi minus pi to 2 pi, or this omega TC, this is pi, this is not pi minus 2 pi, this is pi to 2 pi. Or we can that means omega TC is equal to 2 pi minus pi, that is equal to pi, and this is the period for which this diode is reverse bias, that means from pi to 2 pi. But the that time period is 2 pi minus pi, that is pi, or we can say TC is equal to pi by omega radians per second. Here if we see the wave shape, that means here we are getting the output voltage only from 0 to pi, and from pi to 2 pi our output voltage is 0. That means we can say that our output voltage is oscillating, that means from 0 to peak and then back to 0. And thus we can say we are not getting that steady state DC value. That means here the output voltage that we are getting in case of we are obtaining in case of single phase half wave uncontrolled rectifier, that is oscillating, not steady state. Also, if this output voltage is connected to a DC motor, its operational characteristics will be different from if a battery of the average output voltage Vm by pi is connected to it. This is because here we do not have any negative cycle. This means that there will be no torque, because during negative cycle current will be 0. That means there will be no torque, or we can say we obtaining low speed during this period. Also, if a transformer is connected during input side, saturation of transformer, saturation of core transformer core occurs because of the accumulation of flux, because the current is present only in the positive cycle. That means there will be accumulation of flux during positive cycle, and during negative cycle, since there is no current, we are saying that means no current is given back. Basically, normally it happens that during positive current accumulation of flux occurs, and during negative current that flux is given back. Since we don't have any negative negative cycle, that means no giving back of flux occurs during negative results in the saturation of the transformer core. Therefore, there will be more iron losses, there will be transformer heating, and this may reduce the transformer efficiency. So, because of this unidirectional current, that means we are getting current only during positive cycle, and during negative cycle the current is zero. Because of this unidirectional current, we are not using in those circuits where we are using we are using transformer, because this causes saturation of those of core. Saturation of core of transformer, resulting in the losses. Now, second one is single phase half wave uncontrolled rectifier. That means again we are using one source voltage, again we are using one diode. But in the previous case, that was purely resistive load, and now we have purely inductive load. Here also I naught and V naught represents the current and voltage across the load. Again here the source voltage, because it's the series circuit, the source voltage will be Is will be equal to I naught. Moreover, here whenever we are applying positive voltage, diode will be conducting. That means diode will be conducting only when the anode terminal is positive with respect to cathode, and it will be negative only when anode terminal is negative with respect to cathode. Now that means since we are applying the source voltage that is sinusoidal, here the peak will be at omega t is equal to pi and 270. Again, this is the first cycle, this is the second cycle, and for two cycles I am representing here. Now this is the analysis of this purely inductive load. That means here this is the source voltage so when we're applying the source voltage, that means this diode will be conducting, because anode is made positive with respect to cathode from omega t is equal to 0 to pi. Firstly, I am taking the case that is from 0 to pi. That means some current will flow in the circuit, and because of that current I naught, there will be some voltage V naught. Or we can say during when this diode is conducting, that means output voltage, because here the power semiconductor device diode that's taken ideal, and the voltage drop across that will be equal to 0.7 volt, or we can say Vt is equal to 0. Here this minus Vs plus Vd, that's equal to 0, plus V naught is equal to 0, because here voltage across inductor is represented by V naught. That means V naught will be equal to Vs and Vd will be equal to 0. Since we know that V naught is equal to Vs is equal to Vm sine of omega t, or we know that voltage across inductor that is represented by V naught, or VL, that is equal to L di by dt, that is equal to Vm, or di by, on integrating, this is di from initial value to final value from 0 to omega t, as we don't know up to which period that it's conducting. That's why from 0 to omega t. That means our I of t is equal to Vm by omega L 1 minus cos of omega t. Or we can say at omega t is equal to pi, this I of t is equal to I maximum is equal to 2 Vm upon omega L. Or we can say during positive cycle, this inductor gets charged. Since this I of t current is equal to this, or we can say from 0 to pi, where we are obtaining, that means our, because of that driving force, that means because of that source voltage, inductor is charging our inductor is charging, or we can say diode is conducting, and that current reaches its maximum at the peak pi, with the I of t is equal to twice Vm, with the peak equal to twice Vm upon omega L. Here this is represented by, because from 0 to pi, and at this pi omega t is equal to pi, current flows, it's exponentially rising. That's why I'm showing not straight path, I'm showing some curved nature of this. That means it's exponentially rising till it reaches its peak at omega t is equal to pi. That peak is represented by green pen here, that is equal to twice Vm upon omega L. This is the peak, and this I am showing that current is increasing during the positive cycle. Now what happens to the inductor during the negative cycle? Now, if we see that during negative cycle, this Vs is basically rising starting from 0 at omega t is equal to pi. This again the source voltage becomes negative, but the voltage across this inductor is basically voltage across this inductor is very high, or we can say this is more negative as compared to the source voltage at omega t is equal to pi. Or we can say the anode diode, the terminal across the diode, that this anode, if this is anode and this is cathode, this anode terminal is less negative as compared to cathode terminal, mm, because of that inductor that has stored its energy that is more negative as compared to its source voltage. Or we can say diode is again forward biased. Once again I am speaking that this diode is not reverse bias. That means during this negative cycle, this is again forward bias, because this anode terminal is less negative and this cathode terminal is more negative. This diode is conducting during positive cycle as well as during negative cycle. Or we can say during positive cycle, energy across this inductor gets stored, and during negative cycle it gives back that energy to the to this source. That's why I am showing here the voltage across diode, that is during positive as well as negative cycle, that is represented by 0. That is voltage drop for all the two cycles is equal to 0. And this, since our output voltage is equal to source voltage, that's why I am showing that this output voltage follows our source voltage. If this is its source voltage starts from omega t is equal to 0, this output voltage will also start from omega t is equal to till it where we have maxima and minima of source voltage, exactly we have maxima and minima of that output voltage, because our output voltage is equal to source voltage. This current, basically this current is increasing and that's reached its maximum. And now during this negative cycle, this current, basically this inductor provides back this energy, and that's why I am showing this inductor decays its energy till it reaches 0 again at omega t is equal to 2 pi. And once again when the cycle next cycle starts, again this inductor starts charging, and now again after omega t is equal to 3 pi it starts discharging. And this happens, that means discharging during positive cycle, charging during negative cycle, discharging. This happens in this purely inductive load. Or we can say for this purely inductive load, since we are obtaining the purely sinusoidal output voltage, the average voltage for this inductive load will be equal to 0. This is the analysis part of this uncontrolled rectifier for L load, where we know during positive cycle there our output voltage will be equal to our source voltage as the diode is short. That's why I'm representing here V output is equal to Vs from omega t is equal to 0 to pi, and V source, since we know that our waveform, that means from 0 to pi, our we have positive cycle, or we can say V output is basically our voltage across inductor, that's equal to source voltage. Since our source voltage is positive, that's why I am writing here V output is equal to VL will be equal to Vs is equal to positive. That means VL, that is equal to V naught is equal to L di by dt, that is equal to positive. Or we can say this is positive only when the current is increasing. That's why I am showing in that graph current is during positive cycle it's increasing. From omega t is equal to pi to 2 pi, we are saying at omega t is equal to, firstly this is the at omega t is equal to pi, our output voltage is equal to 0 because source voltage is 0. Or we can say L di by dt is equal to 0. This di by dt is equal to 0. This is slope is 0 only either at its minima or its maxima. Or slope is, that means that this slope is equal to 0, that will be omega at omega t is equal to pi. We can say there is a peak of that current, or current is at its peak. Similarly, from pi to 2 pi, basically the source voltage, as source voltage becomes negative, or we can say voltage across inductor, that is equal to V output, that's equal to negative, or L di by dt negative. Current, this differential is negative only when, or we can say current is decreasing. Similarly, at omega t is equal to 2 pi, again the source voltage becomes equal to 0, or we can say at that point current is equal to minima. That's why I'm showing here in the graph, from at 0 is equal, at omega t is equal to pi or 2 pi, the current peak is at omega t is equal to pi, and current will be 0 at 0 and 2 pi. This is represented by that analysis part also, or we can say this current is increasing till it reaches pi, and then it's decreasing it's to reach 2 pi, or we can say the inductor energy is stored in the inductor, and from pi to 2 pi energy is discharged by the inductor, or we can say law of or we can say law of conservation holds here, when energy stored is equal to energy released. Or we can say that current lags behind the voltage by an angle of 90. This is from 0 to pi. We now output greater than 0, I output greater than 0, or we can say power is greater than 0, or we can say power is transferred from source to load. From pi to 2 pi, V output less than 0, I naught is greater than 0, or we can say P output less than 0, or power is transferred from load to source. This means that whenever there is inductor present in the circuit, our diode will conduct beyond pi, whatever be the polarity of the source voltage. We can also say that this inductor behaves like a current source. That means whenever it's supplying energy from pi to 2 pi, basically it acts as an active element. Now these parameters, that means V output average, since this is the sinusoidal waveform, that will be equal to 0. I naught will be equal to Vm by omega L. This V output RMS, since this is sinusoidal wave, it will be equal to Vm by root 2. Since here during positive cycle and during negative cycle, during all the cycles, our diode is conducting. That's why we are saying that this conduction period, that gamma d, that's equal to, we cannot say it's up to 2 pi. We can say gamma d is conducting for all time for this purely inductor case. Here extinction angle will be equal to 2 pi, because here current flows up to angle 2 pi. Since the circuit turn off time, as diode is not getting here, diode is not reverse biased, is always conducting, or we are not getting any reverse biased diode. That's why here circuit turn off time is equal to 0 in that purely inductor case.